So we're going to start off chapter 2 talking about exponent properties, but we're going to specifically talk about rational exponent properties and then also radicals and how to simplify radicals and how the two ideas go together. So our first concept we have to remember is that if I write base b raised to the rational exponent of 1 over n, that could be rewritten as the nth root of b to the first power in that case, but we know that the power can sometimes change. The second example here is b to the m over n power, could be written as always the nth root of b raised to the m power, or notice the other thing you can do with that power is you could bring it into the radical and apply it to the base b, and it's still going to be the same simplification. So depending on whether you want to simplify something in your brain or on a calculator, depends on what form you would rather have it in. And if you're using your brain, which we're going to do a lot of today, you want to use the easiest form possible. So remember our exponent properties. When we are trying to multiply bases together that have existing exponents, we add them. When we divide the bases, we subtract the exponents in that particular order. When I raise a power to an existing power, I multiply. If any base has a negative exponent at the end of the problem, that means we have to move that negative exponent term to the other side of the fraction bar, which I think it's called a manipulum or something weird. It has an actual name. Anywho, it becomes positive once you do that. And then anything to the first power is just that particular base back again. And then remember another rule that we sometimes see is anything to the 0 power is simply going to reduce out to a coefficient of 1 because you have no variable component left and just the coefficient remains. So there's some other exponent rules that we think about. They just kind of make sense once you look at them. So if a is raised to the x power and a is also raised to the y power, that means that x and y have to be the same thing. They equal each other. So again, this is just another example of those exponent rules. And then this one down here is that radical rational exponent transformation rule. So that should feel familiar from your experience in algebra. Again, there's some more exponent rules. This is in chapter 0 of your book, which is like that fake chapter where we talk about a bunch of things that we should have known before pre-calc, but it's been a while. So let's take a look. And actually, let's go to our worksheet. So worksheet 1A, we're gonna give you a rational exponent first. I wanted to change it into a radical, and then I'm actually going to have you take it further, and we're going to simplify the radical. So remember, when you have a rational exponent, top number here is the power, and the bottom number is the index of your root. It says index, sorry. So this becomes the 6th root of x to the 7th power. Now you can put the 7th power out of the radical with parentheses around it or inside. Because I'm going to have you simplifying us right now, I want to bring the power inside with x to the 7th. So we're going to take it further and simplify. So this is further than what you did in algebra for sure. If you think about 6 rooting something, any group of 6 could escape the radical, if you will, and simplify and come out of the radical. So what if I rewrote this as the 6th root of x to the 6th times x to the 1st? Isn't that the same thing as x to the 7th? So the reason I rewrote it that way is because now if you think about taking these 6 roots separately, the 6th root of x to the 6th is just x. And then the 6th root of x to the 1st, that doesn't simplify, so I'm going to leave it inside the radical. So the simplification of that rational exponent is x times the 6th root of x. There's a rule coming up soon about when we have to use absolute value bars. This might be extremely new to you because I don't think we did this in Algebra 2. So the rule is you're going to have to use absolute value bars around the variable. Let's see, how are we going to word this? Let's see. When the original power is even and you have an even root. So original power is even, and then we take an even root, but the result is odd. Okay, so when those three things happen, so when you have an original power that's even, you take an even root of it. We'll see an example in a second. And then I get an odd powered result. I have to use absolute value bars around it. The basic idea is, even though I know there's a plus or minus aspect to like x squared, for instance, when it comes out of the radical, we have to assume that we were just looking at the positive versions of that, because you can't have a negative pop out of an even radical. That's not how they work. So it's coming up. It's not this next example, but I think it's the one after that. Watch me lie to you. I don't remember what the next example is. All right, so here, we're going to rewrite it as 10n inside the fifth root this time. So fifth root, that's the index. 10n is right here, and it's being raised to the third power. It's kind of boring. That's kind of it. Actually, you know what? I don't think this is the same example as your worksheet, so I'm going to actually cross this off. I'm kind of looking at the new worksheet here. Your number 2 is something totally different. It's 4x raised to the 4/3 power. Sorry about that. Year 2017, I'm using the old one. All right, so we have this time I'm going to write down here. We have the cube root of 4x, it's wrong color, raised to the, where are we at? 4th power. So same idea. This is how I rewrite it as a radical, but I want to simplify it. So I'm going to leave it as the cube root, but inside the cube root, I'm going to rewrite groupings of 4x so that I can simplify part of it. So what if I separated it into 3 of the 4x's with an extra 4x kind of off to the side to the first power? Because that's the same thing as 4x to the 4th power. Well, the reason I did that was because we took the cube root of 4x quantity to the 3rd power. These would just cancel each other out, and then a 4x would come out in front of the radical. And then inside, we still have the cube root 4x to the 1st power. You don't have to put parentheses around it like that anymore because it's all inside the radical, so it's grouped unnecessarily in parentheses, but that's okay. So notice I didn't bother using any sort of absolute value bars in my final answer because it wasn't an even root. It was an odd root, cube root. So you don't even have to consider absolute value bars when it's an odd root. So the next one I want to look at, and this is a little note about using absolute value bars. When you find an even root of an even power and the result is an odd power, okay, you must use absolute value bars. So the original one has to be even, the root has to be even, but the result has to be odd. So here is not one of those. I'm looking at your new worksheet and I'm trying to figure out the first time. Okay, so these problems aren't on your worksheet anymore, but this one is. So let's take a look at this. It's going to happen right here. So we have a square root. We're going the other direction now. We have a square root. You don't have to put a 2 in the index, but I like to put a 2 in the index. And this is 64 n to the 6th power. And then instead of raising it all to the 1st power, I'm just going to leave that part off. But let's talk about this. When I square root 64, that's easy. That's just 8. But when I square root n to the 6th power, notice I have an even root, an even power originally, but the result is going to be 6 divided by 2, which is 3. So normally in Algebra 2, you guys would just write down 8 and then n to the 3rd. But because n to the 3rd is an odd result, what we're going to have to do is we're going to have to put absolute value bars around the n to the 3rd power. Here's the issue, guys. If I said, because of the plus and minus issue, like let's say n was -2, I'm making that up. But if I put a -2 into the 6th power, I'm going to get the same answer as if I put +2 to the 6th power. But I can't consider the -1 once it pops out of the radical because you can't throw a negative in front of a square root and then say it's the same answer. You have to force it to be positive, which is why we're putting absolute value bars around the n to the 3rd. All right, and then the next example on your worksheet is this one. So we have the cube root of 8m to the 9th power, but this is all being raised to the 2nd power. So it's up to you when you raise it to the 2nd power. I think I'm gonna go ahead and square everything right away. You don't have to. You can do it at the end, but it's not too bad to do this. This is now the cube root of 64 m to the 18th power. And then again, I have an odd root, so I do not have to worry about absolute value bars. The cube root of 64 is a 4. And then the cube root of m to the 18th, when I divide those, is m to the 6th. So again, I don't need to worry about absolute value bars because it was an odd root. There's no more absolute value bar examples coming up here, guys. But if I just throw some down, because there are quite a few on your bookwork that you're going to do. So if I have like the square root, or you know what, let's be fun, 4th root of a to the 12th power b to the 8th power. So normally in Algebra 2, we divide that index into the powers. So that would be a to the 3rd power, b to the 2nd power. But notice a to the 3rd power has now an odd power. So I need to put absolute value bars around just the a to the 3rd. You don't have to put them around b squared. You wouldn't have to take the absolute value of b squared because if it was negative for b, when you square it, it becomes positive. So it's forced to be positive regardless. Notice there, guys, we started with an even. We took an even root, but we ended up with an odd power. That's why we had to use absolute value bars around the a to the 3rd. All right, here we are going to use our properties of exponents more than likely, and then we're going to try to simplify it. So exponents on top of exponents, we're going to multiply those together. Actually, you know what, guys? This isn't even in your notes, but let's do it anyways. We're already here. This is x to the 9th. All right, moving on. All right, so here we have rational exponents. So same properties of exponents, but we're going to have fractions. So watch out. First thing I look for is any snuck in there coefficients, and I notice you have a 2 and a 3. So my new coefficient is a 6. And then I look for any like bases that I can combine using exponent properties. So this is x squared and then x to the 1st, which becomes x to the 3rd when I add them together. And then now for the fun one. I have y to the 4/3 and y to the -1/2. So I'm going to have to add 4/3 plus -1/2. I realize you guys have calculators, but you know what? You should be able to do this without a calculator. Your SAT test is half no calculator. A lot of the college entrance exams require you to take a no calculator basic skills test, and it's like riddled with fraction and decimal work. So just to remind us how we add and subtract fractions, we need to get common denominators. So I'd multiply this fraction by 2/2 and this fraction by 3/3, so it's out of the common 6 denominator. This becomes 8/3. You don't have to say plus a negative, but it is plus a negative. What did I just say? Oh, jeez. 2/2. No, 3/3. 3/3. So minus 3. Jeez. I quit. All right. Too early in the morning, guys. All right. 8/6 plus a -3/6. And when I add those together, I get 5/6. After I just went on like a rampage about how you should be able to add fractions together, and then I can't even add them myself. All right. So there's nobody who's negative. We're going to talk about what happens when you have a rational exponent in the denominator in a minute also, because that means more work for us. But this is our final answer right here. All right, same idea here, except this isn't on your worksheet anymore, so we're going to skip it and moving on to, this one is on your worksheet. So power raised to existing powers, we're going to distribute it to each power, and then we're going to multiply them together. So this becomes x to the, let's see, -2 times 3/2. The 2's would cross cancel, and you get -3. So x to the -3 times y to the, 2/3 times 3/2 is reciprocal, is just a 1 when they cross cancel. Nothing happened with the existing x squared or y to the -2. But I am going to need to combine those together. So combining my x's together by adding them, I get x to the -1st. And then same thing with the y's, adding them together, I get, that's magical, y to the -1st. Neither one of them can stay where they're located because they're both negative exponents. So we're going to need to flip or reverse this fraction around. The x and y are now in the denominator. There has to be a 1 in the numerator to indicate that they're in the denominator, so you need something as a placeholder there. All right. The next example I see on your updated worksheet is, you know what, I think the next one on your worksheet got changed a little bit. So it's not this one anymore. Number 7 on your new worksheet says b to the 5/4 to the 3/2, raised to the 3/2 times u times v to the 3rd. All right. So distributing this 5/4 times 3/2. Let's see, you know what? That's kind of a bummer because there's no cross cancellation, but that's all right. We just multiply the numerators and the denominators and get 15/8. So this is v to the 15/8. And then this is u to the 1st and v to the 3rd. So there's no collection for the u to the 1st. There's no other like base, so just u times all these dudes. We're going to need to add those together. So 15/8 plus 3. So common denominator here would be an 8. The first fraction already has it. Give it to the second fraction. So this becomes 24 over 8 instead of that. So 15 plus 24 is 39 over 8. So this is v to the 39 eighths power. Lovely. All right. Oh boy, this next one. Next one's going to be a good time. I'm going to erase this work off to the side here. I am also, for the sake of time and effort and space, I am going to kind of skip over the how you add and multiply fractions, without a calculator. So I'm just going to tell you what the results are. But please, if you're getting ready to take an SAT test or any sort of NCSM or ASVAB test, that you practice how to do fractions a little bit by hand on your homework. All right, so we have some distribution in the denominator. The numerator, nothing exciting happens, but I'm going to write it as u to the first v to the 3/2 for now. And then down in the denominator, when I distribute the 1/3, I have u to the 2/3, v to the negative 2/3, and then there was an already existing u to the 3/2, v to the 4/3. So that denominator is a hot mess right now. I'm going to collect some like bases. For instance, the u to the 2/3 and u to the 3/2. When I add those together, I get u to the 13. No, that's not right. 13/6. That doesn't sound right. You know what? I gotta try this again. All right. So whoops. 2 over 2. This is a 3 over 3. So that is a 4 plus. Let's say 9. Yeah, that is 13 over. I double guessed myself. All right. So we have this u to the 13 over 3. No, 6. Gosh. Okay, apparently I need to use my calculator. Times v to the negative 2/3 plus 4/3. I got that one. That's 2/3. So there's my new denominator. And my numerator is still u to the first times v to the 3/2. So now I'm going to use my subtraction rule that says when your bases are being divided like this, you subtract them. So 1 minus 13/6 would be 6/6 minus 13/6. So that is negative 7/6. And whenever you use that subtraction property, the answer defaults back to the numerator. So it's up top for now. Similarly, we're going to use that same property for the v's here. So 3/2, which is 9/6, minus 2/3, which is 4/6, that is 5/6. So using that negative exponent property, anything with a negative exponent is moved to the base. So right now we have v to the 5/6 power over u to the 7/6 power. Technically, this is an inappropriate mathematical answer. There's some rule out there in math that says you can't have a radical in the denominator. So we're going to do what's called rationalizing the denominator. And we used to do this all the time in geometry with the square roots. We just hit top and bottom by a square root. And that's because if you have a square root, that's the same thing as 1/2 power, right? So if you just give it another square root, those exponents add up to a whole number of 1, and you no longer have any sort of a radical in the denominator. Well, ours are more complicated because we still need these exponents to add up to a whole number, but they're not cut by halves. This particular problem is cut by 1/6. So I have 7/6 right now. The next whole group of numbers for us, okay, so like 6 over 6 would be a whole number, 12 over 6 would be a whole number. So I got to get it up to 12 over 6. So think about how many more do I need to make 12 over 6? I need 5 more. So I'm going to multiply this denominator by u to the 5 over 6, and I'm also going to multiply the numerator by u to the 5 over 6. So this is what rationalizing looks when you have really funky radicals on the denominator. Numerator is fine, like you just write down v to the 5/6 times u to the 5/6. They won't combine because they're not the same base. But down here in the denominator, when I add those exponents together because they have the same base of u, that's 12 over 6, better known as 2. Voila! I no longer have a radical in my denominator. Right. That's a tricky thing, and we took that out of the Algebra 2 curriculum because it's so much fun, but we need to be careful. All right, let's look at number 9. So we have some distribution. I'm going to do my work up here, though. Apparently I'm going to run out of work. This is x to the negative 4. This is number 9, by the way, on your worksheet. X to the negative 4 over, when I distribute everybody with a negative 2 power, I get x to the negative 2, y to the negative, nope, positive 4 now, hello. And then x to the negative 5 halves. I'm not going to move anybody around or subtract anybody until I clean up this denominator. So this is x to the, negative 4 over, let's see, negative 2 plus negative 5 halves. Let's see, that's negative 4 halves minus another 5 halves. I mean, you could say plus negative, but whatever. Negative 9 halves. So x to the negative 9 halves. This y to the 4th, nothing happened yet. But when I go to subtract my x's, right here, my x exponents, I have negative 4 minus, careful, a negative 9 halves. So this is negative 8 halves. Double negative would change to a plus 9 halves. And I get 1 half. So this is x to the 1 half. But I did that subtraction rule, so that's in the numerator. And anything with that y to the 4th. So he is still in my denominator. And that is actually a good answer. So no rationalizing necessary on that question, but the next one we do, spoiler alert, will totally have rationalization. Number 10 on your new worksheet. All right, so I noticed some addition right here with the x's. I'm going to go ahead and add those together. So that becomes x to the 4 halves plus 3 halves is 7 halves. Leave the y for now. Worry about him in a second. And then when I multiply 4 times 3 halves, I get something. I get x to the 6. Yeah? Yeah. All right. So 2 things. We need to subtract this, and then we need to move that guy. It's got a negative exponent with nobody to collect. So 7 halves minus 6 would be, remember 6 is like 12 halves. So that's negative 5 halves. Blah, wah, wah. So both of, oh gross, both of these are going to get moved to the denominator. So we have 1 over x to the 5 halves, y to the 1 half. Both in the denominator, which we know we can't have. So we're going to rationalize, but we're going to kind of do them separately because they're own little rationalization questions. So think about how many more of these, how much more of an exponent would I need to get to the next whole number? Well, for halvesies, that's easy because every half is the whole number. So I just need another y to the half to get to my next whole number. Now for the 5 halves, again, just every half is going to get you to a whole number. So if you give it 1 more half, that'll bring you to 6 halves, which is a whole number. So this is x to the 1 half as well. So this becomes, up top we have x to the 1 half, y to the 1 half. But down in my denominator, be careful, I have x to the 6 halves, which is x to the 3rd. And then y to the 2 halves, which is y to the 1st. You can put a little 1 here if you want. This is my rationalized answer. So don't go through and then go subtract them again, because you're just going to end up with that like non-rationalized answer that we had over there. So that's your answer. Just leave it. I'm not going to make you rationalize tons of questions. I don't really care about that skill for pre-calc. But what I am worried about is if you go to an SAT test or a college test or even the back of your textbook, you're going to notice that if you didn't rationalize, none of your answers are going to match up. And I want you to know the equivalency and why that is. All right. Actually, you know what? I think that's the end of our lesson. So there's some other examples of how to break down radicals. This one's super fun. This is from your textbook. The 10th root of 32 over the 6th root of 2, and they want you to rationalize the denominator again. So remember, if this is like 2 to the 1/6, if you give it 5 more 6s, that'll bring you to the next whole number, right? So that'll be a way for you to rationalize that example. It's not the most exciting question. There's a lot of simplification in that question. I'm actually not going to ask you to do that one, I don't think, so don't panic. This is from the book, but I would like to talk about this one just because we need to know when we use absolute values and when we don't. So if I could take the 4th root and kind of break down these variables into groupings of 4ths and then the leftovers. So like 21, for instance, would be the same thing as x to the 20th with another x to the first. Oops. That would be the same thing as x to the 21. And then for y to the 15th, that would be the same thing as, let's see, y to the 12th with 3 more left over. Now the reason I broke them down that specific way is because when I take the 4th root of x to the 20th, that's x to the 5th. We'll come back to that idea in a second. And then when I take the 4th root of y to the 12th, that's y to the 3rd. And then in the leftover part of the radical, I still have that x to the 1st and that y to the 3rd. So then the question becomes, do I need absolute values or not? Remember what the rule was. Even root, which we did have, but the original power has to be even. The original power has to be even. Neither one of these were even. I know when I broke them apart, they turned into even powers, but you have to look at the very original part. There is no way that you could have something that's negative to the 21st power inside of a 4th root and have a real number. Not going to work out that way. You'd have I. Okay? So leave absolute value bars off of this one. All right. I think, you know what, that's enough examples for this lesson. Plus, my class is about to start. All right. Good luck.